In this video, we continue with the formalization of motion planning problems from the geometric perspective. We start by defining two concepts, the workspace and the configuration space. The workspace is the stage on which the action takes place. For robots acting in the physical space, such as manipulators, the workspace is three-dimensional. However, sometimes we can simplify the problem and use projections to smaller spaces. For example, if we were planning for vehicles that move in the plane, we could use a two-dimensional workspace. If we're trying to coordinate the motion of two trains on the same track so that they don't collide, we could take the workspace to be one-dimensional. We'll use the workspace to keep track of the obstacles with which the robot should not collide. We partition the workspace into two subsets, W-free and W-collision. W-collision is a subset of the workspace that is occupied by obstacles. W-free is the subset that is free of obstacles. This partition can be described by a function from the workspace to the booleans, returning true if the point is inside an obstacle and false if it is not. This partition is all we need to consider for the environment if our goal is to avoid obstacles. In other robotics applications, robots must manipulate and affect the world by touching it. Think of a robot butler opening doors or a robot surgeon making incisions on a body. For those applications, we will need much more complex representations of the environment. Let's see what the workspace representation could be for solving motion planning problems in Ducky Town. Imagine taking a 3D scan of a Ducky Town. The occupied parts are W-collision and the unoccupied parts are W-free. If we thought that we could solve the planning problem in 2D, we would only need to define a 2D workspace. There is something subtle here. The 2D workspace is in general not the projection of the 3D workspace to the 2D plane. If we were to project the 3D obstacles to 2D, we would get a projection of the traffic light to count as a planar obstacle. Instead, what we would need to do is to measure the height of a duckybot and take the slice of 3D space from the ground to the duckybot height, and then project the slice to 2D. In that case, we could only see a small portion of the traffic light in the 2D map being part of W-collision. That is in fact the part with which duckybot could collide. As you might have noticed, in robotics, we want to keep the dimensionality of the problems as low as possible because lower dimensions means better efficiency. In some cases, the workspace is technically 3D, but it is sufficient to project it to 2D for planning. For example, consider a city built on hilly terrains, like Rome. As a car drives around Rome, its altitude and 3D orientation change. So you might think that we need to use 3 dimensions. However, we could project the hilly terrain to the plane, as we do when making a map. The problem is effectively 2D. Notice that this projection will not preserve distances at a large scale. That will be something to take into account later. If there are tunnels or overpasses, we cannot project to the 2D plane, but still we could avoid using a 3D formalization. The situation could be represented by what is called a two-dimensional manifold. You can think of that as the collection of many patches of 2D space joined together. If the world is dynamic and there are moving obstacles of which we can predict the motion, then we can generalize the formalization to allow for spatiotemporal obstacles. The partition of the workspace into W-free and W-collision will also depend on time. We can visualize the situation using space-time diagrams. An obstacle is now its temporal shadow. If we have uncertainty in the raw motion prediction, we can enlarge the shadow to obtain a conservative approximation. We will now define the configuration space C of a robot. The configuration is a subset of a robot state relevant to the motion planning problem. The configuration space C could include just the vehicle's pose or pose end velocities. For a duckybot, we could take C to be SC2, the set of planar rotor translations, at least in theory. For example, this duckybot here was not happy to stay in SC2 and wanted to explore all the possibilities that SC3 can offer. If we were planning for n robots, then the configuration space would be SC2 to the n. The occupancy function is the map from the configuration space to the subset of the workspace that is occupied by the robot. For example, for a duckybot, the occupancy function is a map from SC2 to a subset of R2 that is the shadow of the duckybot. This subset is sometimes called the footprint. We have defined workspace, configuration space, and occupancy functions. We can now write a formula that describes the non-collision constraints. At each time, the intersection of the robot footprint with W occupied should be empty. Note that now we can take a trajectory in configuration space and verify that it is collision-free. Different robots and other agents in the world could have different configuration spaces. If we have the occupancy function for each of them, we can check if there's a collision by checking that the intersection of their footprints is empty. In this video, we have introduced the concept of workspace, configuration space, and occupancy function. With this concept, we can formulate the non-collision constraints in a motion planning problem.